Welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. In this module, we will continue our discussion on communication in a distributed system. So, in the last class we defined what is a reliable communication, and then we discussed about the types of different groups, and we looked at the various mechanisms which are unicasting, multicasting and broadcasting, and decided that multicasting is what is the most useful mechanism to use in distributed as well as cloud computing, and we looked at the correctness criteria for a multicasting. In this class, we will understand the concept of reliable multicast, and then we will discuss how far correctness criteria that we defined in the last class are applicable, obeyed by a reliable multicast, and then we will go ahead and understand how correctness can be made a part of a reliable multicast. First let us define a reliable multicast. A reliable multicast is a multicast which guarantees that each message, this is a group communication, so there will be multiple processes which will be sending messages to each other. So, in this system, each message that has been sent to the group will eventually be delivered to each relevant process in a uncorrupt form. So, the system is gives a guarantee. What guarantee does it give? That each message that has been sent to the group will eventually be delivered. So, delivering immediately as soon as it has been sent, it will immediately be delivered, that is not the guarantee, but the guarantee is that it will be eventually delivered to each relevant process. That means that if it is meant for a set of systems processes which are part of a group, only they will receive the message and in an uncorrupt form. So, the message should not be corrupted. So, let us look at an unreliability in multicasting. An unreliable multicast will be in a very basic form. It will be a system which attempts to deliver messages to all the participating process. However, there is no guarantee of arrival of the correct message in each process. That guarantee it does not give. Does it mean that it will never be correctly delivered? Not necessarily. If the best case comes, then correct message will be delivered by all processes, but the messages may be received by some processes, but not all the processes, and the message may be in a corrupt form. The unreliable multicast does not make a guarantee. So, if an application chooses to, in a system like cloud, if an application chooses to use a unreliable multicast and it says that I am not interested in it using a reliable multicast, then what will happen is it will be on a best effort basis. So, a best effort basis does not guarantee anything, but if it is possible, they will deliver it, but if something goes wrong, there will be nobody to take care of anything that may go wrong. So, who will provide this unreliability? In a normal system, it is unreliable. So, somebody has to take care of bringing reliability into the multicasting environment. Who will do it? Typically, in a cloud like environment, the service provider will provide. So, if an application, if the SLA or service level agreement of an application requires that the multicast communication be reliable, then it is the responsibility of the service provider to guarantee reliability, or otherwise if the application has not opted for a reliable multicast, then the application level itself can provide a reliable multicast. So, what is correctness? Let us look at that, as we have already seen in the last module. Correctness has three criteria: that all the nodes or processes of the group should receive a message sent, and the complete message and that means half the message has been delivered and the other half is not delivered, is not acceptable. So, the complete message must be delivered, and if there are multiple messages sent by one process or many processes are sending different messages in a group, then the messages should be delivered in order. Now, if we look at the definition of reliable multicasting, then we see that the first part is guaranteed. All nodes must receive the message or messages. The second point is also guaranteed, that the complete message, because reliable multicast gives the guarantee that all processes will receive a message sent and the message will be in an uncorrupt form. So, these two will be guaranteed. What about the third point, that it should be delivered in order? Unfortunately, a reliable multicast does not guarantee that messages will be in order. So, what we should do about message ordering? We have to have an additional mechanism using which we will guarantee that the messages are also delivered in order. So, let us look at the ordering of in a multicast mechanism. Each process in this multicast environment may receive various messages from in any permutation of the messages sent. So, where applications need an order, that means it is important for the application that the messages are delivered in order. It needs to further specify what kind of ordering is required, and the service provider must guarantee that. That means an additional check on the ordering also has to be included. Reliable multicast alone is not sufficient. So, what are the possible orderings that is possible? Is it always the sender's ordering? It is not always the sender's ordering. In fact, if you look at a distributed environment, many times it is not even possible to have an unique sender's ordering. So, these are the possible orderings. One is the unordered. So, the application does not expect the provider to give any ordering. That is the best effort that we said. The second is a FIFO order, which is the first in first out order. The third is a causal ordering, and the fourth is a total ordering. So, any one of these four will be guaranteed by the service provider. If the application needs total ordering, for example, the application will specify in their SLA, the service level agreement, that total ordering is required, and the service provider will have to provide total ordering of the reliable multicasting. So, now let us look at what we mean by a specific ordering. So, let us first look at the unordered multicast. Here in example, where we have 5 systems, 5 processes P1 to P5, and P1 is a process which is sending 5 messages M1 to M5 to the other 4. They all 5 form a group. So, P1 sends these 5 messages, and P2 is the first process which receives the messages in some order, and P3 receives the messages in a different order, P4 in a certain order which is not the same as P5, and this is completely all right. This is reliable unordered multicast. So, the messages are received by the receivers in different orders than what is sent by the sender, but this is an unordered reliable multicast. The next one is the FIFO order. As we understand from the name, it is a first in first out order, in which the multicast from a sender are received by all receivers in the order they were sent. So, this is the formal statement of FIFO ordering. If process P sends 2 messages MI followed by MJ in that order, then each process in the multicast group will be delivered the messages MI followed by MJ in that order. So, the sender's sending sequence will be retained in terms of delivering the message. So, this is in its same example. We have P1, P2, P3, P4, P5, and P1 is sending 5 messages M1 to M5, and if it is sent in the order M1, M2, M3, M4, M5, then FIFO ordering ensures that P2 receives, P3 receives, P4 receives and P5 receives. All of them will receive in the sender's order. Only then we can call it a reliable FIFO ordering, a reliable FIFO multicast ordering. In case there are multiple senders, there is no restriction on the way the messages from different senders will be received by the receiver. So, let us take an example P1 and P2, and P1 sends 2 messages M11 and M12, P2 sends 2 messages M21 and M22. Now, the correct ordering according to FIFO will only ensure that P1's 2 messages are delivered in the correct order and P2's 2 messages are delivered in the correct order. It will not worry about the intermixing of the P1's message and P2's message. So, M1112 followed by 2122 or M11211222 or any such M2122 and then followed by M1112 are absolutely perfectly fine. However, we see that if it is M12 followed by M21 or M22 followed by M21, then it is not a correct order. So, in this example we see that M22 and then it is followed by M21, and in this example we see that M12 followed by M11. These are incorrect examples and are not acceptable. So, the ordering of the sender will be respected, but different processes will receive. So, these orders are correct, which means that one process will receive the messages in this order, a second process will receive the message in this order, and it is perfectly fine. Any of these can be used to any one of the members of the group, and it is a correct order. The next one is called causal ordering. Causal, the word it's pronounced as causal, and it has come from a cause and effect relation, where we say that the multicast whose send events are causally related must be received in the same causality obeying order at all receivers. So, there are some important terms here. It is causally related. We have to understand the meaning of what is causally related. So, formally it can be said like this, that if a message Mi results in the occurrence of a message Mj, then Mi will be delivered to each process before Mj. So, if Mj is an answer to a question asked in Mi, or Mj is a response to the message given by Mi, then Mj will have to be delivered after Mi has been delivered. So, that is the requirement of a causal ordering. So, why is it required? Say, let us consider any cloud based bulletin board in a office, where they have various, they have offices in various cities in an organization. So, if one staff makes a post by message M1, which says maybe something like, I think our office should be closed on Saturdays also. Now, this message will be delivered to all the people who are part of the bulletin board. Now, if another colleague replies with a message M2, which says that, but that is not a fair demand, then whoever has not seen the first message should not see the second message, because the second message, that is not a fair demand, is in response to the first message that the office should be closed on Saturdays. If that message is not delivered, then delivering the second message is not correct, is inappropriate. So, causal ordering ensures that when two messages are coming from two different processes, then they ensure that these two messages will be delivered to a third process in the correct order in case the second message is in response to the first message. So, in this example, it is imperative that M2 must be received by all recipients after they have received M1, otherwise M2 will not make any sense. So, here is an example where P1 is sending a message M1 to the group, and say assume that P3 does not receive the message. So, P2, P4 and P5 receive the message M1, but P3 has not received the message M1. It has not received yet. Now, P2 in response to M1 sends a message M2, and M2 will be sent to all the processes. If M2 is received by P3, P3 does not understand the message M2. So, the order in each one of these will be that it will be M1 followed by M2. It will be M1 followed by M2. But the order in this is that it first receives M1 and maybe at some point in time later on it will receive M2, and this is not appropriate. This is not correct. So, in causal ordering, in case there are two messages which are dependent on the second message is dependent on the first message, then the system has to ensure that the first message is delivered to all the recipients and second message will be delivered only after the first message has been successfully delivered. Now, let us extend our example and let us think that P3 is another colleague who supports P2 and sends a message M3 saying that I support P2 completely. Now, in this, all receivers must see P1's message, then they must see P2's message, only then P3's message will make sense. So, they have to see that P1 had sent a message M1 saying that the office should be closed on Saturday. P2 has sent a message saying that that is not a fair demand, and then P3 says I support P2 completely, that it is not a fair demand is useful or meaningful to the process. Now, let us look at a variation of causal ordering. Let us consider that M1 and M2 are two processes, two messages sent by process P3 sends a message M3 in support of P1 rather than P2. We take the example of for last example and make a variation of it. Now, M3 says I support P1. In this case, we are not sure whether P3 actually has seen P2's message or it has not seen P2's message. That means that M3 is not causally dependent on M2 because it has seen P1's message and it is replying to P1's message. So, here the dependence, the causal relations are M1 must be received before M2 and M1 must be received before M3, but there is no relation between M2 and M3. Therefore, M1, M2, M3 is a good causally relevant related order, but M1, M3, M2, this second example is also a correct example and is a correct ordering according to causal relationship. So, causal ordering ensures that if any message is causally related to an earlier message, then those messages must be delivered in order. Now, these messages may or may not be sent by the same process. But in a causal ordering, all messages sent by the same process are considered to be causally related. They are causally ordered. So, therefore, we will just continue with the earlier example. If M2 and M1, so M1 M2 cannot be violated and M3 M1 cannot be violated. So, therefore, these are all wrong. Now, as we were discussing that when a process sends a set of messages, we consider all these messages to be causally related or causally ordered. Therefore, causal ordering have to be implemented on a process order. So, if a process has sent 5 messages, it remains in causal ordering. It is imperative in causal ordering that all these 5 messages will be delivered in the order in which the process had sent. Now, if 2 processes are sending a set of messages, then in FIFO we said that there is no need for making any relationship between these two. But in causal, we need that the messages sent by 2 different processes will still have a relationship between them if the message has been sent by the second message has been sent by the process after seeing the first message. That means a message is in response to an earlier message received. Such pairs or such groups have to be ordered and have to be delivered in that order. All the rest of the messages can be delivered in any order, as we have seen in this simple example of ours. The last one is the total ordering. In total ordering, this is also called an atomic ordering. As we have already seen in many examples, that atomicity is the practice of all or none. That means whenever we say an atomic ordering, we insist that somewhere the changes or variation cannot happen. So, in atomic ordering, we don't really put any restriction on the sender's order, unlike FIFO. In FIFO, we said the sender's order is important. Even in causal, we said sender's order is important. But in total ordering, we do not worry about the sender's order at all. But it ensures that all the receivers receive the multicast messages in the same order, irrespective of the sender's order. So, put it formally, in an atomic order multicast system, all messages are guaranteed to be delivered to each participant in the exact same order. The same order is not the sender's order. The same order is some order. Note that the delivery order does not have to be FIFO or a causal, but must be identical for each process. So, that is what needs to be guaranteed in total ordering. So, this atomic or total ordering only guarantees that messages sent by the same process, however, will be considered to be sacrosanct. That means, if a message is sent, if 2 messages are sent by a process P1, these 2 messages will never be disturbed, but all other messages, even if there is a causal relationship, atomic ordering does not really bother about that. They will reorder, they can easily reorder all the messages in any which way and they will deliver it. So, no guarantee on different senders orders. So, here is an example. P1 sends M1, P2 sends M2 and P3 sends M3. An atomic system will guarantee that the message will be delivered to all processes, all receivers in only one of the 6 possible orders. So, it can be M1, M2, M3, M1, M3, M2, M2, M1, M3 and this and this. So, any which order, but P1 is receiving this order and P5 is receiving in this order and P7 is receiving in this order cannot happen. So, all the messages that will be received, some predefined order will have to be guaranteed, and using that all the messages will be ordered and will be sent. No predefined requirement is there, except for the fact that a sender, if the same process is sending two messages even in atomic ordering, that cannot be violated. This is what we call a sender's a process order. If a process is sending more than one messages, then that has to be guaranteed. Others can be easily reordered, but all processes receiving the set of messages must be seeing all the messages in some order which is identical to each other. So, the delivery will be identical for each other. So, here is another example of atomic multicast. Say P1 sends M1 and then M2. P2 replies to M1 by sending M3. So, there is a causal relationship between M1 and M3, but M1 will not be bothered to be in relation to M3. So, no ordering on M1, M3 or M2, M3. Where ordering will be imposed? Between M1 and M2, because they have been sent by the same process. So, M1 has to be received before M2, but other than that no other ordering is really required. M3 can however be interleaved with these messages in any manner. So, a correct order will be M1, M2, M3 or M1, M3, M2 or even M3. If we note, M3 actually is in response to M1, but total ordering does not guarantee anything. So, M3 may be received after first and then M1 and M2, but M2 followed by M1 is an incorrect order. So, when we look at, let us understand why atomic multicasting is actually required. Many times the sender's order is really not important. There will be many applications where the sender's order is not important, but the importance lies in the fact that the processes, the participating processes must follow identically, must ensure that everybody is following the same set of instructions. If we take an example that if there is a set of jobs that one has to do, and these jobs are being done by a group of people, they will all be executing that set of jobs. The result, the outcome of the application of these set of jobs must be identical. How these jobs have been evolved, they really do not worry about the ordering of the jobs. So, these jobs will be given by these processes to all the participating processes, and these processes must ensure that the set of jobs must have been applied in the same order, and this is defined by atomic multicast. There will be some examples, some applications where the correct order, the FIFO order must be maintained. In some applications, they do not want to restrict it to FIFO order, but they want to ensure that in case there is a causal relationship, that must be maintained. Even a third set of applications where neither of these are required, but some order you decide, forget about the sender, you decide some order and apply that order to all the receiving processes. So, to summarize this module, we observe that multicast may either be reliable or it can be unreliable. In reliable multicast, we guarantee that the message sent will be message received, and all the processes in the group will, in the multicast group, will receive the message. A reliable multicast must ensure that only the first two correctness criteria are maintained, that the message will be received by everybody and a message will be received in an uncorrupt form. Therefore, the reliable multicast must be further extended for ordering of the messages to make it a correct reliable multicast. In that, we looked at unordered, where no guarantee is given to the ordering of the messages. We looked at FIFO ordering, where we said that the order of the senders must be maintained by the receivers. That means, in any order that the senders have sent, that must be completely obeyed by the receiving process. We looked at causal multicasting, where we said that if there are more than one senders, then don't worry about the respective orders of the messages unless one message is in reply to the other message. And we looked at atomic multicast delivery, where we said that it doesn't matter what order the messages will be received, but do ensure that all the recipient processes are able to receive all the messages in the correct order, in some correct order. So, these are our references. Thank you.